In this module, we're going to talk about decision tree and also training. VLSI design just like going through a maze, need loads of decision making. In the decision tree model, a VLSI circuit design will involve 3 layers. The first layer or layers is structure. That means you need to pick up the structure for your design. In the second layer is really determine the parameter or device parameter in the structure. And finally, you have to verify the design. And if a design doesn't meet your requirement, you have to going back and fine-tune your design. So as a summary, with a circuit design decision tree, we have the structure layer, we have the parameter decision layer, and verification layers. So now let's use the struct layer to define the entropy. In the struct layer, for example, for a simple MOS amplifier, we have 5 choice or called solution space. In the decision make, depend on your design requirement and also design knowledge, each option with associated with the probability P1, P2, P3, P4, 5. So now on this decision tree, we can define the entropy of the decision make by this equation. That means this is a summary of all of the possibility P and also log MP, log 2P. So now let's use a parallel decision to explain the decision tree and entropy and also probability relation. For two decision tree, we'll have 2 choice. That may be the probability P or minus P. Here is a plot to give a relationship between entropy and also decision probability. First one, if at the beginning of the design, you have no clue of your decision, so your probability will be half and half for each options. In this case, we have the maximum entropy of 1 bit. During the design process, so now you are leading to one position. In that case, P is not equals to half anymore. In this case, your entropy also reduced from 1 bit. At the end of decision, you already pick up the correct selections. In either P equals to 1 or 0. In this case, your entropy will be down to 0. So here is showing the decision of two parallel decision case. That means at the beginning, you have maximum entropy. At the end of the project or decision, you have minimal entropy. For n-bit n-selection trees, in this case, the maximum entropy is happening if all of the options have equal probability. In this case, your entropy will be log 2n bit. The entropy also can be defined for distributed solution space. In that case, the entropy is also proportional to log of the solution space size. Next, let's look at introducing the concept of decision tree training. Okay. Decision tree can be trained to minimize entropy by gaining the information. For example, for any decision tree like this, at the beginning, if you have no clue at all the P will be equal. In this case, we'll have the maximum entropy. We'll call entropy 1. At the end of training, by using design information, we can tune P1, P2, and Pn to a low entropy state. In this case, entropy will be reduced. Okay, at the end of a project, one of the options, for example, in this case, option 2 are picked for your design. In this also, at the end of the tuning, the information gain will be stored inside this decision tree. Of course, in VLSI circuit design will be in the structure, parameter, and also verification layer. And also the information gain equals to the entropy reduction before and after training. So now let's look into the different training families. The first thing we're talking is a direct training. In this training, we'll rely on the feedback from the leave cell to train the coefficient. This could be a full decision tree or a part of decision tree branches. Starting a training is sequential and usually will be slow because they need feedback to do the training. But the good side is starting a training have good accuracy because you are training the decision tree itself. Again, the information gain will be stored inside the decision tree. This will including the structure of decision tree, the parameter of decision tree, and relocation of layer of decision tree. In some of the training could be partial. That means you are not relying on the final node of the decision tree, but you are doing partially. So you can do a local training. Second family of training or called indirect training. This are usually training really rely on the information gained from a replica. In this case, if I want to train this decision tree, we can use a replica to train and passing the coefficient to the decision tree you want to train. Okay. Certain training also could be full decision tree or partial decision tree. Also, we can using past information, let me train historically or learning, or we can use current training that are gained from a direct training replica. The good side of such training is it can be really fast because you can use information from history. However, it might suffer from the limitation of the accuracy due to the mismatch between the decision tree and its replica. In practical design case, many of VLSI design are rely on combination of direct and indirect training. So now let's look into what kind of information we can use in the VLSI design. In the traditional design method, the information can be used from manufacturing process technology information, or from design specification, or from the designer's experience and learning, or from the simulation and verification result, and also even done from the field testing. In this class, we'll be focused on advanced design information, rely on symmetry principle, structure, and method. And these are information gained based on universal replica.